What I'd like to do today is an introduction to the MQTT protocol, also look at how we can design clients and servers in software, and then how we can make a scalable system. Pardon me. The MQTT protocol, or Message Queued Telemetry Transport, was developed by IBM and has now been released royalty-free, so it's free for anybody to adopt, and has actually become an ISO standard. It's a very lightweight protocol, so it's ideal for small constrained devices. Typically sits within an TCP packet, and that will very easily, as we'll see, match onto any TCP/IP stack or module. It has been designed to support a very wide distributed network, so it becomes robust against frequent network disruption, devices appearing and disappearing off of the network. So over the last year or two, it's started to become one of the established ways of connecting IoT devices together. One of the big attractions about MQTT is that it is simply a transport. It doesn't really force you to packet your messages in any particular format, such as XML or JSON or anything like that. So really, you can transfer your data between devices simply as an array of bytes, and then it's up to your application to interpret that data. So we have a simple transport which you fill with data, and as a header on that, we specify a topic. So this is a label that says what the data is, and it really becomes as simple as that. We can then send the data, and it will be sent out to any node that's interested in it. So this gives us a very easy, lightweight way of moving data between our devices. So MQTT is based around a publish and subscribe protocol. So sitting in the middle, we have a server, and this is called a broker. So devices can connect to the broker, and then they can publish their messages. So here we have a topic that we've designed, and we can publish that into the broker. We don't have to configure that in advance, so we publish to the broker. If the topic doesn't exist, it will create an entry for it. So the broker is automatically maintaining a database of our messages. Once the broker has then received a new message, it will publish that message to any of the nodes that have subscribed to it. So all of our nodes are connected to the broker via a TCP packet. So they connect and then hold open a TCP socket, so they can then publish and listen to new data that's been published. So this gives us quite a simple system, and in practice this is extremely fast. Where we've published data from a small node, it's appeared almost instantaneously into an MQTT client sitting on the PC. So we can publish out to a remote broker sitting on the internet and receive back the data extremely quickly. So inside the broker, we maintain a list of these topics, and these topics really we define for ourselves, and they are just a set of sort of a system like how you would describe a file system. So below here we can say home/room/sensor/temp. So we can publish, we can define, easily define any of our topics in this format, and then any remote nodes can subscribe to those topics. They can also use wildcards, so it's possible to subscribe to a range of topics and receive updates as soon as any of those have been changed. Now, in terms of developing a broker, there's a widely used open source MQTT broker called Mosquito. So that's you can simply download, start running on your PC, and then you have a Mosquito server, an MQTT broker running straight away. We can connect to that, publish and subscribe to messages that are put on it. So it's very easy to build up a local system and start experimenting very, very quickly. There is one other file. There's a configuration file that goes alongside the Mosquito server that then allows you to set up accounts, passwords, and also encryption certificates as well, which we'll see in a little bit. Now, in terms of talking to the Mosquito server, there are a very few number of methods that we can use. So we simply connect to the server. We then have methods to publish and subscribe. We can unsubscribe, we can disconnect, and we can also ping the server and clients as well. So this gives us a very small number of methods to implement, and hence a very lightweight stack. When we do come to publish and subscribe to a message, we have a quality of service indicator as well. So when we subscribe, we can give a quality of service from 0 to 2. At 0, it's just a best effort transport. So when a new data is published to the broker, it will publish out to all of the subscribed nodes, and it will just transmit once. If they lose it, then the data is lost. If we go up to level 2, then we get guaranteed delivery and no duplicates. So again, we have a choice of how we want all of our nodes to listen to methods, and those are easy to mix and match. There is also a version of MQTT for sensor networks. So here we have a very lightweight protocol that runs, it's designed to run over RF networks. This talks to a gateway which has a full MQTT client, which then talks back to the broker. So within a local area, we have some very lightweight sensors running low power applications, talking back to a full MQTT client that then communicates to our broker and allows remote applications anywhere on the internet to then access that data. So to look at implementation, we have a very small C client that we can add to our device, and this is very easy to adopt to different network transports. So any TCP stack or other method that we're using to send IP packets, we can very easily hook onto. To get started, as I say, we have the Mosquito server that we can download and install. There are also a number of MQTT clients available as well. One that we've used and found to be quite easy to use is MQTT.fx, which you can download. This gives you a simple client where we can connect to a Mosquito server. We can then publish and subscribe messages. So it's quite easy to build a PC-based test system, which we can then check that the system is working before we start to use our small embedded nodes. There's also a number of public brokers that are available on the internet for testing. One that we've used is at IoT.eclipse.org. So here you are allowed to freely connect to it, publish any data, and subscribe to that data. So again, it's a very good service for just playing around and experimenting with MQTT to begin with. In terms of our client software, probably the most widely used client is an open source client called Farho. I think this again was originally developed by IBM. But it's now published on www.eclipse.org/Farho. So we can download this, and it's a small collection of C files that are very easy to port into a microcontroller project. And this allows us to implement the full MQTT client and also MQTT-SN as well. The website also has lots of news, projects and documentation, so it's a very active area. We can it's worth a look and to regularly connect to it to have a look at any new information that's there. So when we build up our project, so here we have a Kyle-based project. We've added the 10 files, which are the Faho clients, and again, those are pure C files, so they just build very easily, and you don't need to do any porting work with them. At the bottom, we've added the Kyle networking component, so we have to start with a wired Ethernet connection. And one of the nice things here is that we can enable DHCP. So when we take our client, we can put it onto the local network. It will lease out an IP address. So again, in a real application, a customer wouldn't have to configure the node. And also we have a DNS client, so that we simply need to provide a URL of the remote broker, so that when the node starts up, it leases out DHCP, and then when we connect to the broker, we can get its IP address. So all an end user would need to configure would be the URL of the broker, and that's the sort of thing that most people understand anyway. So it makes setting up our system very, very easy. So now to connect between the MQTT clients and the TCP/IP network, there's a single file which is the MQTT Transport layer. So this is a small collection of functions that we need to add code to connect between the MQTT layer and the TCP/IP networking layer. So these are a small collection of functions, and they map very easily onto BSD sockets. So we have a single command to send, we have one to get data, and a non-blocking one to get data, and then commands to open and close. So in a simple system, most of these functions contain pretty much a single line of code that is the matching BSD socket command. So again, this is almost trivial to do. So here in the transport where we're opening the socket, in the red, we're using the Kyle DNS client to get the IP address of the host. So here we're just passing the URL, looking up the IP address. And then the code in blue is setting up the BSD socket and connecting to the remote node. So if you're not familiar with BSD sockets, this looks a bit weird, but this is pretty much the standard code to open a BSD socket. So then once we've made a connection, we can start to publish and subscribe to MQTT topics within the broker. So to fully make that connection, we have the client data, so our client string, the password and username, the version of MQTT, and then the URL and the port that we're going to connect to. So then within the MQTT client code, there's a function to serialize that connection. So we pass that data, and it will then flatten that out and turn it into an MQTT packet, which we then simply call the transport and send that packet. So we connect to the server, and then we can send packet buffers. We can then read back, and we should get an acknowledge from the broker that we've established a connection with the broker. So here we're also connecting to port 1883. So this is the unencrypted port on the Mosquito server. So this is an easy way to get up and running, but at the moment all of our code is running in plain text. So it's not really a practical system, but it's a first step to experimenting with MQTT. So now we have similar functions to publish MQTT messages. So we can have a payload. We can think up an arbitrary topic. So again, here we just make up a string for the topic that we want to create. And then we use the serialized publish function to take that data and flatten it and convert it into a packet of data that we can then publish to, so that we can then send to the MQTT broker remotely. So that will now take this data and publish it into the Mosquito server. And then to subscribe is a very similar process. Again, we take the topic that we want to subscribe to. We have a serialized function that will take that data and create an MQTT packet, which we can then send via the transport up to the Mosquito server. And here we should get an acknowledge, which tells us that we have subscribed to that particular topic. We can now go into a loop to monitor the TCP socket, so that when the MQTT broker publishes, we will get a packet, and here the packet read will tell us that we've had a publish message. We can then have another function to deserialize that packet of data and convert it back into useful data. So here we can get things like the topic, the payload, the quality of service, the message ID, etc. We can then take that data and go and use it in our application. So we just have a handful of functions now that we can create topics, we can publish them up to the broker, we can subscribe, and then any nodes that have subscribed will receive that data every time it's updated. Now that system is fine. As I mentioned, that's an unencrypted connection, so it's quite good for just experimenting and playing around with the system. But in a real application, we need to add security. So here the established way of doing this is with transport layer security. So this provides an endpoint-to-endpoint encryption between the clients and the Mosquito broker. We can do this, and we've run a previous webinar on the Mbed TLS library, but this provides a full TLS encryption library. And it's designed for small footprint microcontrollers. So it's very modular and will fit down on most modern microcontrollers. It's published by ARM as under an Apache or GPL v2 license, so it's free to use, free to download, and it's used across a number of different platforms to provide TLS security for our devices. So here in the Kyle tools, the Mbed TLS is provided as a software pack, so we can integrate it into the tool chain and then add it to our system. And there are a very large number of files in here, but with one configuration file. So again, we just have to set up the configuration file to give us the appropriate level of TLS security that we want. We then have our same transport, and we now can create a TLS thread that will handle the TLS handshake, and we'll also need to hold some certificates that are used during the TLS handshake as well. So here we've just added these as C files, which in a real project would be bad practice. You would need to have some way of holding those in a file system or a separate method of installing them into internal flash in a real project. But again, if you want to have a look at Mbed TLS, it's available at mbedtls.org. Now, when we're looking at using TLS security, whenever we currently connect to a secure website, we're establishing a TLS connection. And in this case, we're downloading the server certificate, validating that certificate, and then establishing a secure encrypted connection with the server. Now, this is fine if you're running a web shop where you want a secure server, but you want to allow any number of clients, unknown clients, to connect. So in this part of the world, doing server authentication is fine. However, if we're developing an Internet of Things application, we really want to provide a higher level of security. So in this case, we want to develop mutual authentication, where the server has a certificate which has to be validated by the client, And ideally, we want to have client certificates that are also sent to the server so that we can validate what client is connecting. So if we have our own closed system, we then have this authentication where clients will only connect to the server, but the server will only allow authorized clients to connect. So we're getting away from simple password authentication to a full TLS certificate authentication. And these certificates are in a format called X509. And the key items of data that are in this certificate are the subject's public key. So the whole point of the certificates is to exchange public key, asymmetrical encryption public keys, so we can then negotiate a session password for symmetrical encryption. And the certificate has a signature which has been signed by a certificate authority. So within the public key infrastructure, we have a trusted third party called the certificate authority. And here you would give your details to the certificate authority. They would create an X509 certificate and sign it with their private key and give it back to you. And then we would take the public certificate of the certificate authority, and we can use that to validate any certificates that have been signed by their private key. So in the case of Alice and Bob, they can exchange certificates, validate both certificates with the certificate authority's public certificate. Once they have confidence that they've got the real public key of the person trying to communicate with them, they can establish a secure link using the TLS handshake. So this level of certificate-based authentication gives us a very strong level of security, particularly if we're using mutual authentication. Now, there are a number of commercial services. So Amazon Web Services has an IoT platform. Azure from Microsoft also has an IoT platform. So these provide certificates for mutual authentication, or certificate services for mutual authentication. If you're developing your own closed system, there's a useful tool called XCA, which allows you to create your own public keys and become your own certificate authority. So here we can create certificates, we can create certificate revocation lists, and we can essentially manage our own closed system. So within the Mbed TLS, once we've added this to our project, we can add our certificates, and there is a parsing there to support the X509 certificates. So here we can load the CA certificate. The second line we can load the certificate revocation list, and we can also load our client certificate. So then during the TLS certification, we have these loaded into memory so we can pass the certificates to and from the server and the client. And then here, again, this is very reduced code just to give you an idea. We can connect to the server. We can set up the TLS authentication mode, the certificate chain, the random number generator, and then we can start in purple the secure socket session where we create the context, say the host name that we're talking to, and set up the IO level of the Mbed TLS net. And then we have one function called in red, the TLS handshake. So in here, when we connect to the server, this will call the Mbed TLS library and run through the negotiation, the TLS handshake, to establish a secure level of encryption. Once we get through that function, we have a secure connection between the client and the server. So this takes a reasonable amount of time, but we can hold open that TCP link to send and receive messages. The Mbed TLS also supports session cookies, so that once you've made a first connection, we can go through that handshake far more quickly the second time. And then the set basic I/O layer. This really is the mapping between the bottom of the Mbed TLS library and the IP stack. So here again, we're really just mapping onto the BSD sockets. So again, it's quite easy to adapt this to work with any TCP/IP stack or Wi-Fi module, or however we're communicating with the Mosquito server. And then to send our MQTT packets, we prepare them exactly as before. So we flatten them into a buffer, and now we have a couple of functions: the secure socket write and secure socket read. So here we pass the data in, that will encrypt it, and then send it up to the Mosquito server. And likewise, we can read packets that have been sent by the server, decrypt them, and make them available to the application. So although we're adding lots of different third-party stacks, so the TLS, the Mosquito client, the IP stack, it's very layered, and we can bring each layer up independently to check that it's working. So it's not as complicated as it looks at first glance. Now, there are a number of commercial systems, and they all are starting to use MQTT. So this is becoming quite an established way of managing a fleet of embedded devices that we have distributed around the network. So here we have Amazon Web Services. So the front layer provides mutual authentication and an MQTT server. And then you can take the data into the rest of the Amazon Web Services system. There is a very good evaluation board from ST. So this provides a small discovery board. This has Wi-Fi, NFC, Bluetooth, and sub-gigahertz radio. So again, it's got an awful lot of connectivity, and it's also packed with sensors as well. So a number of MEMS sensors, temperature, humidity, pressure, and also a time of flight sensor as well. So it's plus a couple of push buttons as well for traditionalists. So this is a very interesting little evaluation board. And it comes with a project that implements the MQTT client, the Mbed TLS library to connect to the Amazon Web Services IoT, and also support for the Wi-Fi module as well. And this is available in Kyle, but also IR and GCC. So it's a very good starting point to play around with this technology. It's backed up with a detailed application note. The code builds to about 100, just over 170K. So you'll need a full tool chain to experiment with it. If you're using the Kyle tools, there is a 30-day evaluation license that you can request from Hitex UK or Hitex Germany, so that you can use professional tools to build this system. There's also another little application board which has just been announced by NXP. This is based on their LPC 54018, which is again a Cortex-M4 based microcontroller. It comes with a similar Amazon Web Services IoT support. So it's based again on Mbed TLS and the FreeRTOS operating system. Interestingly, the device that's on this board also has some cryptographic hardware as well. So it has an AES, a hardware module for AES 256 encryption, SHA-2 hashing, a hardware random number generator, and also secure key storage. So there's an OTP memory, which is write only, and then only the cryptographic unit can read back. So there is a secure way of storing encryption keys on this device as well. The Mbed TLS library can also be ported to use these hardware features in place of its normal software modules. So we can optimize the TLS to use the hardware accelerators that are on this particular board. At the moment, this is available on the American Amazon website, but doesn't seem to be on the European, or certainly not on the UK one at the moment. But we'd expect it to be available via distributors in the UK, if not now, then in the near future. And it's about, I think, $35 on the American website. But again, this is another very good starting point to experiment with MQTT. There's also a very nice tutorial that's published online as well. So the web link's here, and we'll send out the PDF to you afterwards. But this shows using, again, the Kyle tools with the MQTT client and also the Mbed TLS library as well. So this talks and builds up a connection. I think this one actually talks to Azure as well. So again, a nice starting point. We will be publishing some examples of how to use the MQTT client. So again, if you're interested in these, just raise a question and request the examples, and we'll send them out to you, I would think early in the new year when we have them available. If you have any other questions, please let us know. But thank you for joining us this morning, and I hope that's been useful. It's a very quick introduction, but I must say, when I first started with this, I built the first application. I thought, God, I'll never get this working, talking to an unknown client, a little server on the internet, but it did actually run pretty much first time. So it was quite easy to get going, and as I said, the response is very fast, and it's a very practical way to build up an Internet of Things application and build a scalable system that will connect to a fleet of devices based around the internet.